Hello, I am Ritam and my roll number is MB2321. I am going to talk about the application of the method discussed in our project. The application I applied the method on two things. First, I simulated data, and then I applied on the real life data which is available in R. The reason behind doing a simulation is because we have in hand available the actual configuration of points, and then we can compare it with the MDS solution. So how I proceeded was I sampled 20 samples from multivariate 2 normals, which is in which is into 0 0 and 1 0 0 1. This is the standard normal in 2 dimensions. Then I calculated the interpoint distances, which is the T20 cross 20 matrix, where the Tij is nothing but the distance between xi and xj. So this works as a dissimilarity matrix. Dissimilarity matrices are nothing but matrices with non-zero elements, and DRR equal to 0 and DRS equal to DSR. Okay. So this is a dissimilarity matrix, and for classical MDS solution, from dissimilarity matrix we look for a set of points which satisfy that dissimilarity matrix. So from this set of data, I calculated the dissimilarity matrix or distance matrix, and this looks like this. We can see that distance between same points are 0 and distance between different points are positive. Now, to apply the method discussed in our project, we took help of this following package in R, that is SMACUF, SMACUF. How I proceeded the analysis was, first I looked for datas which are null. So I used na.omit in my distance matrix. Then I calculated the stress function. The stress function is something that has been discussed in the report before. This is the stress function. This is the stress function. So we compute this stress function and then minimize the stress function to get the classical MDS solution. So here we apply jackknife on this stress function, and we get the jackknife solution for this data or dissimilarity matrix. We see that there are 20 observation which agrees with the number of samples I collected. So there should be 20 points, and the value of the loss function after doing the iterations are 0.3585. This is the minimum value, and the stability measured is 0.99, which is very close to 1. So let me remind what is stability measure again. Stability measure is nothing but 1 minus summation yi minus y naught divided by yi square. These are the total variances, and these are the centered variances, where y naught is the averaged out values of these yi's. And what are yi's? Yi's are nothing but the MDS solution when the ith point is not available. The ith point is not available. Okay. And the cross validation is 1 minus n times x naught minus y naught divided by summation yi whole square. X naught is the actual MDS solution and y naught is the jackknife MDS solution, and that is the averaged out values of the yi's, and therefore the cross computes the distance between the actual solution and the jackknife version of the solution. So if cross is not close is not close to 1, that this means this is not close to 0, so which means there is some bias. So we can somehow use this cross validation measure to correct for the bias thing. Then we calculated some plots. This is the jackknife plot. This is the fluctuation of every point for every iteration. So let me just describe one of the points. This looks like a star. In the center there lies the ith point. Let me say this is the xi point. So this is the value of the ith point in the matrix y naught, and for every iteration this denotes the fluctuation of the point. Suppose this is the location of the point in the iteration y1, this is the location of the point iteration y2, this is the location of the point iteration y3, and so on. So these are the fluctuation of the same point for different jackknife iterations. So these are same plots, so I don't need to, and these are just the plotted points from the y naught in two-dimensional plane. Note that the dimension is not being reduced because I purposely collected data from MV2, that is multivariate 2 normal, so I am not reducing the dimension. I could have reduced the dimension to 1, then the entire points would lie on one line. So I did this purposely so that I could see the analysis easily. This is the configuration plot, that is this is the actual MD solution. This is the distribution of stress across the points, and this is the relation between the normalized dissimilarities and the configuration distance. Note that there is a linear relation, that means more normalized distance with that and this implies higher configuration distances in the configuration plots. That is, if the points are further away in the actual case, in the configuration case they will be further away as well. This is the bubble plot and this is the histogram plot. This is nothing but this actually counts how many points are some particular distance apart. Let's say about 35 points are about 1.5 distance apart from each other. So these are just counts. So this is the basic analysis I did with the simulation, and then I will be doing the same analysis using real life data. So I use the data pack Gure from the package R. This package contains the distances between the departmental stores in France. There are 86 total departmental stores, and the matrix contained 86 choose 2 elements, that is it's a 86 cross 86 matrix which contained distances between those departmental stores in kilometers. So from there I again do the same analysis and compute the stress function, and we minimize it and compute the jackknife solution, and then plot the jackknife solution. Here are the plots. These are same things as I explained before. In the middle the point, the ith point in the y naught lies, and for different iterations y1, y2, yn, we map the different fluctuations using these stars. So these are there are too many points and the picture is very small, so they look like single points, but these are actually stars. If we zoom them, we can actually see that. This is the plotting of y naught, and we cannot actually see the names because there are 86 names here. The names of the departmental stores are written down here. This is the actual configuration plot, that is the actual MDA solution, that is from the distance matrix available to us. We computed the possible possible distribution of the departmental stores across the two-dimensional space. This is the dissimilarity versus configuration distance matrix, which also shows a linear relation. Note that if the two departmental stores are about 400 kilometers apart, then in the two-dimensional space their respective points will be 1.5 distance apart. This shows a perfect linear relation. This is the distribution of the stress function across all the points, and this is the residual plot. These are the normalized dissimilarities, and these are the configuration distances between in the actual configuration plot. These are the bubble plots, and these are the histograms as well. And for the summary of the data, if we see that there are 86 objects in total, the value of the loss function is 0.4493 and the stability measure is 0.99. This means that the jackknife solution is very stable. It does not change rapidly in for small perturbations. The cross validation is 0.28, not very close to 1, close to 0. That means y0 minus x0 is not close to 0 as well, and that means there is some bias available in the solution. So we can obviously correct the bias using this cross validation. And that is all for the application. Thank you.